Hello. Welcome back to class. See a few of you are here already. That's good. Say hi in the chat if you're here. I mean, there's only a couple of you. And I hope you have a few questions you'd like to go over today, because that's the plan. Good morning, Liza. Good morning, Navik. So last week of class, can you believe it? All right, we'll get started in about a minute or so. Seems like people may be sleeping in today. It's okay. Good morning, Shutong. Glad you're here. Good evening, Cruz. Oh, yes, you're on the other side of the world right now. All right, well, it's 9 o'clock here in Winston-Salem. I don't know where it is for everybody else, but it seems like the perfect time for the simultaneous sip. So if you have your coffee, your water, or your tea, or whatever, and would like to join in the simultaneous sip, now's the time to do so. Good stuff. You know, we only got one left, so hopefully everybody's there tomorrow to participate in it. Okay, so let me see in the chat. Sam joined in the sip. Good to see you, Sam. Let me see in the chat. Did anybody watch or at least see? Maybe you haven't seen the whole thing yet because it's pretty long. My epic YouTube video that I just made. 109 linear algebra true or false questions that guarantee you ace your final. I had to throw in a little clickbait there to get the eyes, but take a look at those. Took a long time to make. Shutong looked at it. Good. Yeah, I mean, it's just good practice. You know, there's a PDF, and I think I emailed you all the PDF of the questions. So try to work through those. They'll make you kind of a better understanding of the material. It was amazing. Thanks. I have one planned for calculus. It's going to be called Leaked Calc 1 Final. Solved. I don't know if it has the same ring to the linear algebra. Okay. Yeah, but take a look at that. Johannes is here for linear. Excellent. Yeah, so what questions do we want to go over today? Does anybody have any specific topics they want to review today? And you could just say you want to go over maybe a question from a quiz or a question from a test or a test review or something from the book. If you just type, and if you don't want to type out the whole question, I have all the documents. So you could just say, sections 5.1, number 15. And then I can pull it up. I mean, and if you guys have nothing, if you have no particular questions, we could do something. We could do like another example that's similar to what we were working on last week, if that's a good idea. Would you be in favor of that? Can we go over number 4 on test 2? Yeah, let's start with that. And so while I'm getting this ready, think of other questions you might want to go over and just have them ready for when we finish number 4. Okay, so number 6 on test 2 as well? Yeah, we'll do both of those. Okay, so number 4 was let V be a vector space of the functions. So the vector V is the vector space of all functions from R to R. Okay. Okay, so I mean, we've looked at a lot of vector spaces that are similar to this. We've looked at polynomials of a certain degree, and we've looked at, well, last week we looked at continuous functions. This is saying all functions. Okay, so V is the collection of all functions from R to R. We want to show that the even functions are a subspace. Okay, remember a function is even if f of negative x equals f of x. Okay, so that's what it means to be even. Okay, so somebody in the chat, do you want to remind everybody what are the three properties we have to check in order to show that this collection of functions is a subspace? What do we have to check? We don't need to show it's a basis. We could, okay, so that's how to show something's a basis. We want to show something is a subspace. Maybe I was over on the side, so maybe you couldn't quite hear it. So how do we, there was 3 things, right? Do you remember what the 3 things were for a subspace? 3 conditions had to hold. The 0 vectors in it, good, that's the first. And then the next 2 were closed under addition and closed under scalar multiplication. Okay, so we'll start with the 0 vector. And on this question, this was the part that gave everybody the most trouble. So, yeah, good, Liza. The question is, what is the 0 vector in this vector space? The vector space of all functions from R to R. So what is the 0 function, I guess, is a way to word it. So what is the zero function? Any ideas? What function has the property that if you add any other functions, nothing changes? Well, I'll tell you what it is. I think you guys know. The zero function is f of x equals 0. So this is the zero function. It's the function that no matter what the input is, you get 0. Right? So is this function an even function is what the question. Oh, sorry. Is this in, I guess we didn't name this. So I guess we'll call it h. Okay, so is the zero function an even function? Well, let's check. F of negative x. So if we replace all the x's here with negative x, we would get 0, which is equal to f of x. So yes, it is. Yes, it is an even function. Okay, so that was the first part. Is the zero function in h? Well, yes. Okay, the next part is we want to show it's closed under addition and closed under scalar multiplication. Okay, so if f is an even function and g is an even function, we need to show that f plus g is an even function. Oh, I see James joins with the SIP. That's nice. Well, let's see. F plus g of x is by definition f of x. I guess we should start the other way around. F plus g of minus x is by definition f of minus x plus g of minus x. But since f and g are both even functions, they're both in h, this is equal to f of x plus g of x, which is equal to f plus g of x. Okay, and then condition 3, if f is in h, is c times f in h. Okay, and so again, we'll do c times f of negative x, which is by definition just c times f of negative x. But f is in h, so f of negative x is equal to f of x. And then c times f of x is the same thing as c times f of x. Are you happy with this? Are we happy with this solution? I apologize for kind of misspeaking for a while about V's and H's, but are we good with this? Yeah. So what a lot of people did, they got when they saw zero vector, they were thinking, well, what happens if we plug in x equals 0? That's not what it's wanting. The vectors here, the elements of our subspace are functions. So the 0 vector should be a function. Okay, that's important to remember. Okay, so if instead of if V was a different vector space, maybe if it was polynomials, then our 0 vector would still be the 0 polynomial, which is P of t equals 0. Okay, so Sam suggested something else. Number 6 on test 2. Okay. All right, so test 2, number 6. And we could go, I'm assuming you want all 5 parts, Sam. I think it makes sense to do all 5 of them anyway. All right, so we have T goes from P2 to R2. And it's the map T of P of t equals P1, P2. So here I had t's and then I switched to x's, so we should be consistent. That was a mistake. T minus 1, t minus 2, t squared. Okay, so this is all the build up to the question. So parts A and B are asking the same thing, so we'll do them in one go. Show that both of these sets are bases for the appropriate space. So show that B is a basis for P2 and C is a basis for R2. Okay, so how do we show that B and C are bases for these spaces? How do we show that B is a basis for P2? Well, there's a lot of ways we could do it. I think the easiest way to do it is put these into a matrix. So we'll map it to like the standard basis for R3, put it in a matrix, and then use like one of our favorite properties from the invertible matrix theorem to show that it's a basis. So with B, this corresponds to the matrix -1, 1, 0, -2, 1, 0, and 0, 0, 1. I guess we could call this matrix B. I know that's confusing. We're using the same letter over and over again. B hat. Can you go over test 2, 2B? Yeah, we'll do that next. So one way to show that this set is a basis for P2 is we could show that this matrix is invertible. And we could do that by showing it as a pivot in every row and column. Ta-da! Since there's a pivot in every row and column, we have a basis. And then similarly with this guy. I think most of you got this first part right. Okay, so you'd have to reference the invertible matrix theorem. I'm not exactly sure which letter it would be from the invertible matrix theorem, but right, we have a pivot in every row and column. So one of the conditions of the invertible matrix theorem says that the columns of these matrices form a basis for the appropriate space. All right, so the columns of this B matrix here would form a basis for R3, but we know R3 and P2 are isomorphic, so they're the same. They act exactly the same. Okay, so that was the easy part. So let's go to the next part. Okay, so the next part says find M, which is the matrix for T relative to B and C. Does anybody remember how we're going to go about finding this matrix? So the way we did it, basically what we want to do is we want to find the C coordinates of the images of these vectors. So we'll apply, or of these basis elements. So we'll figure out what does T do to each of these basis elements, and then we want to write them in the C coordinates. Okay, so we'll start with T of T minus 1. Our transformation sends our polynomial to, well, the first entry is when you plug in 1. The second entry is when you plug in 2. Okay, and so now we want to find the C coordinates of each of these vectors. And those will be the columns of our matrix for the transformation relative to both B and C. All right, and the way we do that is we take the basis elements of C in all of our images here and make a big augmented matrix. And then we're going to row reduce it until we get the identity, and what's left on the right is M. So I would look back in your notes. So if you had a question like this on the test or on the final, what I would do is just take your book and look into the glossary and say, find where it says matrix relative to bases, or, try to find where this section is in the book and look at the example that we did in class that day about this, because we did one very similar to this in class. So now you would take this matrix and we want to row reduce it until we get the identity, and then what's left over on the right is M. Okay, and so we know how to do that. So I'll pretend you did the row reduction on your own. And what's left over is -1, 1, -2. There's not enough space for this. So this entry here is the C coordinate of T of B1. This is the C coordinate of T of B2. And I don't have the space, but this is the C coordinate of T of B3. So that's how we get these columns. So this here is M. Okay, the next question was, what is the range of T? Okay, one thing you could do for this is you could take M and show that it has a pivot in every row. You could also see that T, two of its images are 0, 1 and -1, 0. These two vectors span all of R2. Right, we know that the range is going to live inside of R2. I mean, I erased it, but the map went from P2 to R2. And since we have two linearly independent vectors, we know it spans the entire R2.
Okay, so the range is all of R2. Okay, and then the last part is what is the kernel of T? Okay, so what is the kernel of T? Does somebody want to say in the chat, just not in this example, but in general, what is the kernel of a linear transformation? Does anybody remember that? All the vectors that get sent to 0. Yeah, exactly. So there's a couple of ways we could do this. We could do this using our matrix relative to B and C, our transformation matrix relative to B and C. But you have to remember that all of these entries are relative to our basis C, okay? So that's not really how we normally think. We usually think in terms of the standard basis. So the way I solve this question, we could do it both ways, but let's start with the way I solve the question. We take a polynomial and figure out what its image is, and then we'll figure out which what do we have to do to the coefficients to make it equal to 0? Okay, because this is just a regular polynomial. Its image, so remember the rules for plug in 1, that's our first entry, plug in 2, that's our second entry. Okay, so what we want to do is we want to solve 1, 1, 1, 4, 2, 1 times A, B, C equals 0, 0. Right, because we want to make our image equal to 0. So this image can be expressed as this matrix multiplication is equal to 0. The way we do that is we put our answer in reduced row echelon form. And so we get A equals 0.5 C and B equals negative 1.5 C. Okay? And so our polynomials are any polynomial of this form. Or so our kernel so for any value of C, you get a new element of the kernel. that says C is in R. Okay, the other way we could have done this is using we could have used M and done the same thing, row reduce it and get an answer. Right, we would have x1 plus 4x3 equals 0, x2 plus x3 equals 0. But here, these would be, okay, so x, our scalars here would be -4, -1, 1. But these correspond to our initial basis vectors. Okay, so really we could write this as any linear combination of -4 t minus 1 minus t minus 2 oh, I lost the negative sign here. So plus t minus 2 plus t to the third. Okay, so any scalar multiple of this. Sorry, t squared. Okay, and you could check. So these came from the basis elements we started with. You could check that these, if you multiply this out, it's exactly the same as this. Okay, that was a long one, but are we happy a little bit with question 6? The important thing to remember is that M, this matrix here, is not in terms of our standard bases. Okay, so a lot of people got to this part and thought that it meant, oh, the kernel are the polynomials that's like -4 plus t squared. But you could check if you evaluate the transformation to those, it doesn't get sent to 0. So it's clearly not in the kernel. But this tells us the weights of our basis that we started with. Are we good? Silence in the crowd. Maybe that's a good thing. Okay, Shutong, you suggested something. You said, can we do... Sam says dab. Good. That's a good reaction. Can we do test 2, 2b? Sure. Okay, so determine whether each of the following is a basis for the span of some collection of vectors. Okay, so, and we had a bunch of different questions. So to find a basis for this, for the span of these vectors, what we could do is we could take these column vectors, turn them into a matrix, row reduce, and figure out which ones are the pivot columns. Okay, so that's one. That's how to find a single basis. That will help us find the dimension and help us answer the other questions. So this row reduces to 1, 0, 0, 0, 1, 1, 0, 0, 3 minus 4, 0, 0. Okay, so the first and second columns are pivot columns. So in particular, the first and second entries of our matrix form a basis for the span of all of the vectors. And so that's what 2b was. Should we try, like, but the other ones were a little bit tougher. Should we do 2c to show that that's a, right, because 2b, unless I wrote this down wrong, those vectors were just the first and second entry of here. So they definitely form a basis for the span because they're the pivot columns. Can we do C? Yeah, let's do C, because C and D were the hard ones. E was, right, E, there's a single vector. So we obviously know it's not a basis for this space, because any basis for this space will have exactly 2 elements in it. Okay? So let's show that C also is a basis, and then by the similar argument, we'll just redo the exercise and show that D is not. Okay, so let's find what the span of these 2 vectors is. This is how I solved the problem. Some of you did it other ways and it worked out fine, but I like my solution, obviously, because it's mine. Okay, so we want the matrix 2, 0, 1, 10, 3, 0, 1, 14, x equals b. We want this to be consistent. Let's find what vectors b make this consistent. Any vector b that makes it consistent is in the span. And anything in the span we could treat as one of these b's. Okay? So let's figure out what needs to be satisfied for this to be consistent. Okay? And so when we do that, what we do is we take a matrix, an augmented matrix. We start with our matrix we started with, and then B will be our rightmost column. And we want to reduce it to reduced row echelon form. because we want to figure out what conditions do these coefficients have to satisfy, do these B1, B2, B3, and B4 have to satisfy in order for us to have a consistent system. Okay, so when we reduce it to reduced row echelon form, so this maybe should be something you should do on your own, but I'll tell you what it gets to. It reduces to this, okay? And so what this tells us is, well, for this to be consistent, we would need x1 to equal 3b3 minus b1. Not a problem. We would need x2 to equal b1 minus 2b3. Also not a problem. The important part is we need these two conditions to hold. We need b4 minus 2b3 minus 4b1 to equal 0. And then we also need b2 to equal 0. Okay, so do we see how we got these equations from our augmented matrix? So the span of this collection of vectors is all vectors that satisfy these two equations. Okay? So any vector that satisfies these two equations is in our span. What we're going to do is show for C, it's the same equations, and then for D, they were different. Okay, so C were the vectors 1, 0, 0, 4, 0, 0, 1, 2, B1, B2, B3, and B4. Again, we'll row reduce. Put it into reduced row echelon form. And we'd get to here. And so again, we'd read off the equations. It'd say B2 equals 0, and B4 minus 4B1 minus 2B3 equals 0. And those are exactly the same as these equations. So these vectors form a basis for the span of the vectors here, which is this set. Okay, so C was a basis. And then for D, we do the same thing. And we get B1, B3, B2, and B4 minus 3B1 minus 3B2. Okay, and now notice our equations. Is B2 equals 0? Well, that's good. That's what we wanted. But this last one says B4 minus 3B1 minus 3B2 equals 0. Oh, sorry, this should be a 3. I think I just wrote it down wrong. And so these equations, the solution set of this system of equations is different than the solution set of this system of equations. Right, so for instance, the vector 1, 0, 1, 6 satisfies these two equations. All right, that's a bad example because it happened to work out. What was the counter example I gave? Well, let's just make it work. Right, 2019 satisfies both of these equations, but 2019 does not satisfy both of those equations. Are we happy with these? Let me get out of the way. So take a look at all the old material and come up with some good questions for tomorrow. I like to be in front of the camera, but I also don't want to block you. Also, if you haven't watched it yet, 109 linear algebra true or false questions to guarantee you ace your final on YouTube. Okay. Yeah, hit the like button before you get out of here. Email me if you have any questions you want to go over. And I haven't decided yet what I'm going to do for office hours on Thursday and Friday, but we'll do something. Okay. I'll hang around for a few minutes if you have any questions. Yeah, last day of class tomorrow. Can you believe it? Can't believe class is already over. Goes by so fast. Yep, that's true. Smashing the like button like a true subscriber, dab. Sweet. Anyone try Mario Kart on Android? No, have not. Great review. Thanks. All right. It seems like class should be over. So, bye-bye.